All right. We need to keep going. I know many of you thought you'd get the day off. Although since it's recorded, you can still take the day off, but we really can't delay. So I'm going to record some short lectures, and that'll make up the whole lecture that I want to talk about today, and that's solving differential equations using Laplace. All right, so last lecture we've already looked at a few. We actually derived some table properties. All right, some Laplace lookup table properties, and today we're going to actually now solve differential equations using those properties. All right, or using those table entries. All right, so let's begin. This will be sort of an intro, couple-minute intro part of the lecture, and then I'll continue to break it up as I have different, as I change topics. But it's all based on solving differential equations using Laplace. Okay, so let's talk about the some very important properties. Okay, to solving differential equation. First of all, we've already seen this actually. The Laplace transform of the first derivative of f of t is equal to s times the Laplace transform of just f of t, and then minus the initial condition, okay, of the function, not lowercase f. Notice that it's a lowercase f, the original f of t, not f of s. All right. So that's fine. We've seen that. Now let's try to expand that. Let's try the second derivative. All right. So d dt squared of f of t. Well, I'm gonna use this property to prove this property. All right. So I think you would agree with me that this is the same as the Laplace transform of d dt and then of d dt of f of t. So imagine, let's call this, like, you could even call this f hat of t. Okay, and then we'll get, so we're really taking the derivative of some function, and I'm sort of hiding the other derivative inside there. All right, so I'm going to set that equal to s, because of the derivative, times the Laplace transform of d dt f of t. Okay, but remember, f hat is really the, and in fact I might just go back and get rid of hat and write dot, because d dt of ft is ft dot. So it's s times the Laplace transform of f dot, let me just write it in that form, of f dot of t, okay, minus f dot naught. Okay, so remember, if you follow this but replace f with f dot, I get s times the Laplace transform of f dot minus f dot of 0. Okay, now I already know, now this is exactly this. Okay, so these two are identical. Okay, these Laplace transforms. So I'm going to just substitute these directly in. So I get s times the quantity s f of s minus f naught minus f dot naught, giving us, and I'll expand and I'll give us the final equation. All right, so let me go to the next page. So I'll expand that. So Laplace of f double dot of t, which is d squared dt squared, is equal to s squared f of s, so that's the Laplace transform of just f of t, minus s f naught minus f dot naught. So as you can see, if you have a second derivative, you need to know the initial condition of both its of f of t and f dot of t. Okay. All right. So now maybe you can see the pattern, but I'm going to now expand this to a general Laplace of an nth derivative. So dn dt to the nth f of t. So the nth derivative of f of t. So you can probably already guess that it's going to be s to the n times f of s, okay, minus the Sn minus 1 times f naught, okay, and then I could do a second one, minus Sn minus 2 f dot naught, and then dot 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 minus s f, let's see, this is going to be f to the, let me write it as, I have to have the derivative, so it's going to be dn minus 1 dt. See, the derivative keeps increasing. There's no derivative, one derivative, 2 dot dot dot, all the way to the n minus 1 derivative times of f, and then the initial condition for that derivative, minus finally the nth, sorry, that's n minus 2. And finally, the last term will be minus no s. As you can see up here, there's no s. But the highest derivative you can go just before n. So dn minus 1 dt f naught. Okay? So I would write dots, but of course I can't do n. I can't write n dots up here, so it would just get pretty messy. So I'm just going to write it as, so this is one term. This is the n minus 2 derivative of f, and then the initial condition. All right. So I think you can see now that an important take from this is that if the initial conditions, okay, if the initial conditions are all 0, then Laplace of dn dtn of f of t is just equal to s to the n f of s. Okay? So in this class we will actually be doing this a lot. Just for practice, we are not going to do that for this lecture. But later, when I describe what a transfer function is, we assume all initial conditions are 0. Okay. But at this point, you should definitely know this equation, just in case I give you a problem with non-zero initial conditions. All right. So let's go ahead and look at an example problem. All right. So let's use these. So here's an example, a very simple example, and here's your differential equation: x dot equals 1. Okay. So let's just be aware that my input is a constant and my output is my x variable. Okay. So I want to solve for x of t. What is it? All right. So this one actually turns out to be really simple. You could do it, I'm going to do it by Laplace, but of course you could go dx dt equals 1, right? And then you get dx equals dt. So therefore you get x of t equals t, or the integral, right? I can integrate both of these. So x of t equals dt, sorry, t, the integral of dt is t, and then of course plus an initial condition, plus x naught. Okay, or sorry, let me double check that. Plus, it's over here, actually. X of t, and I'm assuming this is from 0 to t, and this is also, so this is going to be x of t minus x naught equals t, okay, and that is equal to x of t equals t plus x naught. Okay, pretty simple. Let's do it with Laplace. All right. So if I take the Laplace transform of x dot equals to 1, well, that's equal to the Laplace transform of x dot, which is equal to the Laplace transform of 1. Okay? Well, what is the Laplace transform of x dot? It is xs times x of s. And remember, capital, I always change when I do a Laplace, I always change lowercase letters to capital letters. And the s is because of the derivative. And then don't forget the initial condition, minus x naught. And then, of course, what's the Laplace transform of a constant? You should already know that, or look it up on the table or your notes. It's 1 over s. All right. Now, you might be thinking that, of course, the first method we went through might be the easier method. Well, that's only because this was a very simple differential equation. You can't do this for general differential equations. All right. So let's continue. So now I'm trying to solve for x of s. Okay. So x of s is equal to 1 over s squared plus x naught, or 1 over s times x naught. And that's a constant, so x naught. All right. Okay, so we're really close. All right. So this is, and remember, this is really the Laplace transform of x of t is x of s. All right. So how do we get x of t? We're going to use we're going to do an inverse Laplace transform. All right. We're going to use the tables for that. So let's move forward on that. So x of s equals 1 over s squared plus 1 over s times x naught. Okay. Now, now I'm going to do my Laplace inverse. Okay. Laplace inverse. Okay. So the Laplace inverse of x of s gives me x of t, which is what I'm looking for, which is equal to the Laplace inverse of 1 over s squared plus the Laplace inverse of x naught, 1 over s times x naught. And remember, x naught is just a constant, so due to scaling property, I could pull that out. All right. So we're not going to do any math. We're just going to go to the lookup table and find out what is the pair that matches to 1 over s squared. So we already did this in class, and hopefully you're thinking this is t, and hopefully you're thinking that the Laplace inverse of 1 over s is 1 times x naught, so you get plus x naught. And that completes our problem. So x of t equals t plus x naught. That matches with the first method we solved. All right. So now let's do a slightly more complicated one. All right. Let's move to the next page. All right. Slightly more complicated problem. Hold on one sec. All right. I just got a CU alert. Hopefully you guys are staying safe and are getting these CU alerts. Stay inside. Or don't go by Boulder Creek is what it says. All right. Anyway. Here's an example. All right, here's our classic spring mass damper. Here's B. All right, and let's assume here's mass, and then I've got some force. Let's assume, and let's assume our variable is x. Our variable that describes the position of the mass. All right, position. And this is force. And this is, let's assume we've got some function e to the minus 3t. That's the forcing function. Let's say b is equal to 3, k is equal to 2, and m is equal to 1. All right. So I'm not asking you to derive the differential equation yet, but I'm just going to write it down for you. This is the differential equation that governs this problem. Your differential equation governing your state or your position, and you have your input. All right. So again, what are we trying to find out? We're trying to find out what x of t is equal to. Okay. So first of all, let me also tell you that we have some initial conditions. So I'm going to tell you that the initial position is 0, but the initial velocity is not 0. It's equal to 1. All right. So if we know our initial velocity is 1, and I know my forcing function, what is the output of the position of the mass? All right. First thing we're going to do is we're going to take the Laplace transform of the differential equation. Okay. So I'm going to do it slowly in small steps, I should say. So it's the Laplace transform of x double dot plus the Laplace 3 times the Laplace transform of x dot plus 2 times the Laplace transform of x, which by itself, this is my x of s. All right, by definition. And then the Laplace transform of e to the minus 3t, if you look it up at the table, it's 1 over s plus 3. All right. Now let's clean this up. Well, if we go back to our differentiation properties, you'll notice that this is actually equal to s squared times x of s, okay, and then minus s times the initial position, but that's 0, and then minus the derivative, so it's minus 1. That comes from this term alone. And this term here is going to be plus 3 times s, x of s. Okay? And then you will have s, x of s minus the initial condition, but that's 0, so that can be left as is. All right? Oh, and then plus 2, x of s. All right? So what we'll do is we're going to do algebra to, now that we can actually factor out x of s. Before we could not factor out x of t because it had derivatives. You notice here x of s is now just can just be pulled out. All right, so let's go ahead and do that. So what we get is s squared plus 3s plus 2 times x of s is equal to 1 over s plus 3 and then minus this this 1, so it becomes a plus on this side. So I'm just going to move this minus 1 over to a plus 1, and I'm going to rewrite this as s plus 4 over s plus 3 to get them under a common denominator. All right. So now I'm going to clean this up. Okay. So clean it up, and I'm going to solve for x of s. So x of s is equal to, well, s plus 4 all over s squared plus 3s plus 2 times s plus 3. And that can also be, if I can either factor this, so this actually factors to s plus 1 times s plus 2. So that can be either s plus 4 all over s plus 1 times s plus 2 times s plus 3. Or it can easily be written also, if I factor all those through, it's s plus 4, and then you get s cubed plus 6s squared plus 11s plus 6. Okay? So that's it. That's where we're at. And either of these will be fine, but let's look at this. Okay? We're here. Now the question is, I want to take the Laplace inverse of, well, Laplace inverse of x of t, x of s is x of t. That's not an issue. Okay? But is there a lookup table? All right? Is there a lookup table that will get me from here to some function? And the answer is no. We don't have, obviously we haven't derived one, and you won't find one. All right? So here's the big trick, and I'm going to stop here for this intro part of the lecture, and we're going to continue for the rest of another part. But I'm just going to say that what we need to do, and I'll write it out, we need to break up x of s down into recognizable blocks. Okay. Now you already have recognizable blocks, right? Like for example, 3s minus 5 is the same as 3e to the 5t. Okay, because that's recognizable. And I would say if I take the Laplace inverse. All right, so that's an example. The one we have in the previous page, that is not recognizable. All right, so we need to break it up. So how do we do that? And that's the detail we're going to talk about in the next as I continue to record this lecture. Hopefully some of you are spitting out or saying the words in your head. Hopefully you're saying partial fraction expansion. Okay, which I'll call PFE from now on as I'm lecturing. All right, so that's what we're going to talk about next. Is we're going to talk about we're going to build up and be doing partial fraction expansion so that we can get to x of t. All right, and I'll stop here for this one.